Alright, ladies and gentlemen, we are live recording. So, posed you guys a question. What is the difference in these two motions? You might look at those two pictures and say, they're the same. When in fact, they are actually not the same. Okay? What? That's not what I want you to see if that's what you thought here. Nate. There is a little bit of spinning going on, and when you find out how these two pictures are different, hopefully that will make sense as to why they're spinning. Okay? Alright, so to show the difference between these two pictures, I'm actually going to take you here. Okay? So I set up LabQuest, and I'm going to do a demonstration very similar to what you guys did in the lab last week. I'm just going to toss the volleyball up in the air, catch it, and we'll go from there. Okay? Alright. So I practiced this morning, so hopefully I will get it down. Just in case, just to make sure. I want to make sure that I'm ready to go when the time comes. All right, here we go. And yeah, all right, take two. Back here. It's close. Let's try it again. Oh, that was terrible. Oh, probably that was not terrible. Thanks, everybody. Okay, let's do this. All right, so I am going to zoom this in so you guys can see it a little better. But then also, to help us see it a little better, and if you're watching the video, this makes no sense because it doesn't zoom in when you're on the screen. I am going to zoom in and just analyze this little part of the graph. And we got something that looks like that, okay? And hopefully, that graph looks familiar, yes? Okay? That's the one that you saw when you did the volleyball, okay? First, just to review some concepts. This object is accelerating. There are two ways that we can tell that this object is accelerating. One from the top graph, one from the bottom graph. How can we tell that an object is accelerating from the top graph? Devin, you want to do it? Okay, it's changing in position. So the fact that it is a position graph is important. Cindy, what were you going to say? Good. It is not a constant slope position graph, right? It is a curved line, and that means the slope changes. And some of you, I kind of showed you this on when we were doing the analysis. If I go to analyze, one of the options is tangent, and it'll put a tangent line on your graph, right? So there's the black line that represents the tangent line, and as you can see, as it moves around, that tangent line is a different slope on the top one, right? So when the tangent line changes, the slope changes, and that means that the velocity changes, okay? What's another way that you can tell that this graph is accelerating from the bottom picture? From the bottom graph. Say again? It's going away from zero, but then also what ends up happening to it eventually? Slows down, it comes back to zero, right? Is the velocity graph constant? There are no places in this graph where the velocity is constant, except right here at the beginning. And what was the velocity of the object at the very, very beginning? Zero, because it's right on the x-axis. Okay? So this is a graph of accelerated motion, and we kind of went through what each of those parts mean. Okay? So the one thing I want you to notice about it, though, especially if we put this line in. Alright, and I'm going to go here, okay? So, this point that I indicated on the picture right here is what? What point is that in terms of the motion of the object? That, right? For those of you that can't see Cindy's finger, right, that's the top of the motion, right? Two ways we can tell. One, it's the very, very tippy top of the position graph, right? But what is the velocity value at that point in time? It's pretty close to zero, right? Now, remember that the motion detector only takes data every time it clicks, so the actual top may have happened in between clicks, but 0.026 is pretty close to 0, right? Austin, go ahead.
So in the lab, you don't have to do, when you're doing that, you don't have, and part of the slope and looking for that acceleration.
Yep.
But when you do this, you go analyze and then tangent, and then for halfway, you have to measure and you just want to kind of like go and really roughly halfway.
Hold on that point just for a second, okay? All right, so that's the top of the motion. In terms of this picture though, right? Oh, sorry, you guys zoomed in. The original picture with, the two pictures, right? In terms of those two pictures, first, what shape is the purple graph? What shape is the position graph? It's a math class. This is a math class question. It's an upside down parabola, right? What do we know about parabolas? First, what kind of equations make parabolas? Quadratic equations, so squared equations, right? Okay. What else do we know about the nature of a parabolic graph? You did a lot of this in you do a lot of this in Algebra 2 and in pre-calc if you've done pre-calc already. So. True. This line right here, this black line that I put in here, right? That is a line of symmetry, yes? Okay, does that sound familiar from math class? Okay. Meaning what? Cuts it in half, right? But what's true about the two halves? They're equal, right? They're exactly the same, or they're mirror images of one another, okay? So, onto the left of this black line is the up trip of the volleyball. And to the right of this black line is the down trip of the volleyball. What are you seeing about the graphs on the up trip versus the down trip? Symmetrical, at least from a position standpoint, okay? Velocity, they're pretty similar. Where's my mouse here? Velocity, they're pretty similar, but what's the one difference about the velocity graph before the top versus the velocity graph after the top?
Before the top is the up trip, and after the down trip is the.
How do we know that from that velocity graph, Austin? Velocity is positive on the way up, and velocity is negative on the way down. Okay, but other than that, it's pretty much a straight line from top to bottom, right? Good there? Okay. What's the difference between these two pictures, which you can't see, but if you're looking at the full screen, you can. Right? What's the difference between these two pictures? One's going up, one's going down. Can you tell the difference? Nope, you can't. You know why? Nope. They're symmetrical. Because, first, are these two objects, are these pictures of accelerated motion? Yep. Because what are you seeing about the pictures? They keep getting closer, 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 or farther, 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 depending on whether you're going up or whether you're going down. So this is accelerated motion. But what causes the accelerated motion? First, what kind of accelerated motion is happening on the up trip? It's physically doing what? Slowing down, right? What is happening on the way down? It's speeding up. But what's causing that acceleration in both cases? Gravity. Gravity causes the same acceleration to an object, whether it's going up or whether it's coming back down, right? That may cause it to slow down, or it may cause it to speed up, but the acceleration is the same. Okay? Good there? Two ways we can show that mathematically. Or graphically, I guess. Okay? Let me zoom in a little bit here. Okay? How do we tell the acceleration from a velocity graph? Slope of the velocity graph, right? So, I'm going to take this graph and I'm going to highlight from here to here, right? So just this gray section right through here. Notice, remember, this is you throwing it, this is you catching it, right? This is the part from when it leaves your hands until it gets back to your hands. So at that point in time, what's really the only thing affecting it? Gravity. A little bit of air resistance, but let's go with gravity at this point in time. So I'm going to go analyze, and I'm going to go curve fit, and I'm going to curve fit the velocity graph. I'm going to check mark that box. Notice it just puts brackets around the part that I highlighted. Okay? So, what kind of fit is that? It's pretty linear, right? And what do we see the slope of that graph is? Negative 9.4796. Pretty close to what? Pretty close to 9.8, right? It's negative because which way is gravity pulling it? Down. Acceleration's a vector. It needs direction. That's why it's negative. Because what's the, or you weren't here on Friday, but the value of the acceleration of gravity here on Earth is 9.81 meters per second squared. Okay? Good there? All right. Last thing I'm going to show you on this graph, right? Okay. Up here on the top, I'm going to change this position graph to a graph of acceleration. Okay? Don't worry. Just got to zoom in. Yes.
Beautiful.
You know what? We might just end class right now because this graph is pretty much as perfect as it gets. All right. Wait. I know you can't see this on the video. You must. Big old pat on the back for this graph right here. All right. So, during the time in which this graph is highlighted, what are you seeing about the acceleration graph during that time? Fairly constant, right? Any guess what value it's constant at? Well, let's check it out. So what I'm going to do here is I'm going to go analyze again, and this time I'm going to do statistics instead of doing a curve fit, okay? And I'm going to do statistics on the acceleration graph, okay? And then this window pops up over here on the side, okay? The minimum value during that time is negative 10.2. I'm going to arrow down a little bit. The maximum value is negative 8.7, but the mean value is what? Negative 9.542. And the slope of this graph was negative 9.4, oh, good. Negative 9.4796, right? Pretty much the same thing, because they should be. We're measuring the same thing, just two different ways. We're measuring the acceleration of that object in two different ways. Okay? Austin, go ahead. Use the slope of the velocity graph. Yep. All right, good there. Okay? So, here's why these two pictures, though, look the same, but represent two different motions. On the up trip, the velocity of that object is positive because it's moving upward. But gravity is pulling it which way? Negatively. Whenever we have that situation where we have velocity in one direction and acceleration in the other direction, physically we get the slowing down effect, right? An object is trying to go one way, acceleration is pulling it in the other direction, that's going to cause it to slow down. So, the key points for the first part of those two graphs, when an object moves upwards, acceleration and velocity are in different directions, and that physically causes that object to slow down. So when velocity and acceleration are in different directions, physically we get a slowing down effect. But on the down trip, right? Now that object is moving downward and gravity is pulling it which way? Still downward, right? So if something's already moving in one direction, and then we have something else pulling it in that same direction, physically what's going to happen to it? It's going to speed up. How much does it speed up, though? Well, it depends on where you're at, yes. How much does it speed up relative to the previous picture? 9.81. Or, if we just compare them, it speeds up exactly as much as it slows down on the up trip. We get that symmetrical aspect of the two graphs, right? And if we go back to the graphs, right? During the first part of this highlighted section, right, here, these velocity values are all above the x-axis, meaning they all have what sign? Positive velocities, but where is acceleration in relation to the x-axis? It's underneath, right? So here, during this section of the graph, we have positive velocities, but negative accelerations. And as a result, what's happening to our velocity line during that section? What's happening to the velocity values during this section right here? They're getting closer and closer and closer to what? Meaning physically, what's happening during there? Slowing down. And then, from here to here, right? Velocities are negative because they're under the x-axis. Accelerations are still negative, right? Because it's still gravity. What's physically happening during that section? Well, what's happening to the velocity values? Is this speeding up or slow? This is speeding up. It's just speeding up which way? In the negative direction. Because the bigger and bigger a number is negative, that's actually faster and faster and faster. Right? Good there? And so, right, to summarize, gravity causes an object to accelerate at the same rate, which is always 9.81 meters per second squared directed towards the center of the Earth, regardless of which way the object is going. The acceleration is always downward. And that means that we could cause the object to slow down, but it could cause the object to speed up. But it slows down and speeds up at exactly the same rate. It is a symmetrical trip. If you see the yellow lines that I drew in, did I give you guys the yellow lines on your sheet or no? Okay. If you look at the yellow lines that I've drawn in here, right? The first yellow line is 3 pictures from the top, right? What are you seeing about where that object is? It's the same place, right? It's the same place here versus here, right? It just so happens that this is 3 pictures from the top. This is 3 pictures past the top, right? Same thing with the second yellow line, right? That's 6 pictures from the top. This is 6 pictures before the top. This is 6 pictures after the top. What do you see, though, about where they are? Exactly the same place, right? Same thing's true down here. This is 10 pictures before the top. This is 10 pictures after the top, right? Same place. One's getting slower, one's getting faster. But if we look at it in relation to the top, it is symmetrical. Okay? Good there. Questions? So, right? This we actually just did in class, right? If we draw the position time, velocity time graph and the acceleration time graph, it should look something like this, which it does, right? If we look at those 3 graphs, and we did this already, right? Because, again, wait. So that was because of my stellar ball tossing ability, right? All right.
The new ball was bad.
I did think it was bad, but it turned out, I mean, it really couldn't get much better, right? So if we look, right, acceleration during that time when it's in flight is completely, or not completely, but it's pretty much constant, right? Velocity gets closer and closer and closer to zero, it slows down, but then it goes faster and faster and faster, it goes away from zero and speeds up, right? And then if we switch back to position, right? Nice and symmetrical on the way up as it is on the way down, okay? Even though I didn't catch it at exactly the same place from the time it left my hands till the time it gets back to my hands, pretty symmetrical. Okay? Good there? This applies as long as what's true?
One on Earth and one on Earth, one not one on Earth and one on Earth.
Well, if we did this on the moon, some things would change and some things wouldn't. That's good. Here, let's go here. Cindy, that was good. It wasn't the direction I wanted to go in, but that's okay. So, all right. If we did this on the moon, something would change and something wouldn't change. Discuss with the person next to you. What's different? What's going to be the same? All right. So, what changes about these pictures? The slope of the velocity graph would definitely change. It would be what? It would be less of a slope, right? So instead of being here, it would be, right, we'll do a color that's similar to it. It would be more like that-ish, right? Okay? That's even better because my pen is not lined up properly too inside. But, all right, so it would look more like that, okay? That would cause a couple of other changes. Well, actually, that's not the first change. What would actually be the first change? The acceleration, which would do what to it? Where would it be? Closer to zero, but still where in relation to zero? It would still be below zero, but it would be less than zero, or closer to zero than it was before. All right, so that would be the first change, and that would cause a change in the slope, right? Then what would it do to the position graph? It will do something to the position graph, right?
It will be more straighter.
Mm,
It will up, stay longer, go down.
okay, so it would rise higher because it's not slowing down as quickly, right? If I threw it with the same velocity, it would still keep going up, but it would take longer for it to reach the top because gravity isn't slowing it down as much. So it would go higher, so it would be up higher here, but the middle would also be farther down, right? So it would be right here. Let's see if I can do this. Nah. But those would be the changes that we would see. However, are the shapes any different? Generally speaking, those shapes are going to be exactly the same. Okay? Good there. Yep. Okay. Let's cut it off there for today. There was one more thing I was going to do, but we'll save that actually till next chapter. So tonight, there are some problems dealing with the concepts of the acceleration of gravity. They are all from the Apple book. I will make sure that the answers are posted, but I'm pretty sure they are. So take a look at those. Tomorrow, make sure you bring your course companion, the paperback book, because we're going to do some problems out of there to begin with, and a calculator, because we're definitely going to do some math tomorrow. Okay?